Now, at the beginning of this topic, I said that towards the end of the topic, we will be actually going to the point where what is going on when you go deep down is that a varying magnetic field is generating an electric field. And this is the general form of Faraday's law. Now, in this class, we are going to try to get a feeling of this form of Faraday's law using simple examples. So let's consider the situation here where we have a ring, and this ring is in a magnetic field. The magnetic field does not vary spatially, meaning that its magnitude is the same, its direction is always into the page, and it doesn't vary from a point to a point. However, the magnetic field varies with time. In other words, the magnitude of the magnetic field changes with time. And let me assume that in this case it is increasing with time. But it is not varying from a point to a point, okay? And it's spatially uniform, but varies with time. Now, when this happens, of course, the flux through this ring will vary, and as the flux varies, a current will be, an electromotive force will be induced, and the current will be induced. According to Lenz's rule, because the magnetic flux is increasing, then in this case the current should be in the counterclockwise direction, and so the electromotive force in the counterclockwise direction, and so actually the main cause for the existence of electromotive force and so current, which is the electric field, is there, and it is always tangential at any point. Why tangential? Because when a current is flowing, this means that the charge carriers are drifting and with a given velocity, and the drift velocity is in the same direction as the electric field, and the drift velocities are always tangential to the trajectory. You know, it's the current is circulating counterclockwise. The charge carriers will have at all point will have a velocity which is actually tangential. So this is the direction of the electric field at all points. And we can see also from the symmetry that this electric field should be the same, because, you know, the magnetic field is spatially uniform and it is varying at all points in the same manner with time, and therefore there is no reason for the electric field as a magnitude to be different at different points. Keeping this, having said in this, then this is what we have just said. Now, so the question is, if there were no field, no ring here, but there was a magnetic field that was still varying with time, will there still be an electric field? The answer to this question is yes, because actually the existence of the ring and the current electromotive force in the ring is just a consequence of the field. Because you have a field, and it turned out that there was a current, a ring with free charge carriers, they filled the field and the electromotive force generated, and we had a current. But actually the field existed there. I mean, the ring cannot generate the electric field, because it is the presence of the electric field and the presence of charges feeling this electric field that caused the electromotive force and the current. And therefore, that electric field will still be there, and in the same manner, even if that ring did not exist. So this is the interesting situation that we have. So actually, Faraday's law is not deeply, when you go deep inside, is not about generating a current or electromotive force by a varying magnetic field. It's actually about generating an electric field, even in space, in any region where there is a magnetic field that is varying, even if there is nothing there. Okay, so this is what Faraday's law is about at the micro level. Now let's try to relate, try to find an explicit expression for this electric field that will be generated. And let me assume again that we have this ring also. Now, we remember that the potential difference between any 2 points in a magnetic field is actually given by this integral. This is the definition of the electric potential. Now, in our case, our potential is what is nothing but the electromotive force, okay? And so I can say that in this case, the electromotive force is generated when you consider a loop integral over the whole loop. And so we can say that the electromotive force equal to this and equal to minus d phi by dt. So I re-express now Faraday's law in terms of the electric field now by relating the electromotive force to this line integral of the electric field. In this specific example, this is a very general, by the way, but in this specific example, this is an integral over a path that coincides with this loop. So here it says, Faraday's law, it says what induces actually the change in the flux induces an electric field. This is a quantitative way of saying it, a simplified way of doing this, because doing it formally is a bit more complicated and beyond the level of this course. Those of you who will take electromagnetic theory in the future as a separate course, advanced course, will rederive Faraday's law in a more advanced concept way using vector calculus. But for the time being, this is what we got. Now, on the right-hand side is the change in flux. That's true. But you know what the change in flux here is resulting from the change in the magnetic field, not the change in the area or whatever is that. So this is the Faraday's law in the general form, or this is the general form of Faraday's law, which says that a time-varying magnetic field generates an electric field. Now, an interesting property of the above induced field is that it's not conservative. Why is this? You remember we said that when we discussed potential, electric potential earlier, we noted that when you have, we said that electric field is a conservative quantity in the sense that the work done by the electric force between 2 points is independent of the path and depends only on the endpoints, and the work done over a closed path is 0. So here, if you multiply this by q, this becomes a force and this becomes a work over a closed path. But the right-hand side is not 0 in this case. So in this case, this electric field generated this way is not conservative for this purpose. Now we can go further for the specific example at hand and derive an expression for the electric field that has been generated. We note that due to the symmetry, as I mentioned at the beginning, this electric field has the same magnitude all the time. And also, if I take my integral, my path here to be the ring itself, then in this case, ds is parallel. I choose ds parallel to the electric field, so I can take E outside the integral, because E dot ds will be E ds cosine theta. Cosine theta is 0 all the time because E is always parallel to ds. So you take E outside the integral, you get this expression. Now integral over ds, this is equal to the left-hand side. The left-hand side is minus dBA by dt. This is the flux through the area of the loop. Now, integral over ds is the circumference of the ring, which is E2 pi r. And here, the only thing that is varying is B. A is constant. E has the value B, pi r square, and this is what you get. Arrange things, and you get, this is the expression of your electric field. So the electric field here, as you can see, it is dB by dt. It's proportional to the radius of the ring, and it's also depending on how it's the magnetic field changing in time. So as you can see, E have a magnetic field here changing in time, you generate an electric field. And this is the simple relation between them in this specific situation. Now, here we are going to consider a more specific example and more quantitative example, actually, of, and we will try to find the electric field that will be explicitly, that will be generated by or the vicinity of a solenoid who has the current flowing through it varying with time. Now, we remember that we have found an expression for the field of a solenoid when we talked about the sources of the magnetic field, and it was proportional to the density and to the current. And we know that the magnetic field of an ideal solenoid is actually 0 outside, and it is uniform inside. Okay? And so we have magnetic field only inside the solenoid. We don't have magnetic field outside the solenoid. And when the current is varying with time, so we assume that the current passing through the solenoid is varying with time according to this expression. This is I maximum, the maximum value that it take. Omega is the cycle, the frequency, sorry. Then in this case, we will have the magnetic field within the solenoid, and consequently the magnetic flux with the solenoid will be varying. Okay, so we have a situation where we have a magnetic field that is varying, so we expect to have an electric field generated. Now we want to find the electric field generating outside the solenoid at any point at a distance r from the axis of a solenoid outside the solenoid, and also inside the solenoid. Note that we are looking at outside the solenoid, although we don't have a magnetic field here. So this is interesting. I mean, when you have a magnetic field varying in some region in space, you might have an electric field in some regions where you don't have a magnetic field there even. So that's what's interesting about this situation. Let's calculate actually what is the electric field that we generated here where I don't have a magnetic field, so which is R greater than R. Well, we proceed as usual. Our guide is this equation. We will apply this equation, which is the general form of Faraday's law. And as we have done in the example that we have considered here, we try to find a loop where we can take E outside the integral and then find its value. So in this case also, first of all, let's find an expression for the flux. That's the right-hand side of that equation, which is the flux through the loop. We choose a loop, for simplicity, we choose a loop that is a circle centered at the axis of the solenoid. Why is this? Because we want to make advantage of the symmetry, as you will see. So if we take this as a circle of radius r, the flux through this circle is B, the magnetic field inside, multiplied by pi r square. Note that pi r square in this case is, when you substitute, find the area, it is just the area of the, not the loop, but the ring of a solenoid. Why is this? Because in this part, which is of the circle, which is outside the solenoid, there is no magnetic field. So the magnetic field only exists within the solenoid. So you multiply the magnetic field not with the area of this, of the area enclosed by this loop, no, the area enclosed by the ring, and so of one of the rings of the solenoid with the radius r. So you make it this way. Of course, pi r square are constant, so the only thing that is varying is the magnetic field, which is dB by dt. Now, what is the field of a solenoid? We know from earlier that it is mu naught n, which is the density of turns, multiplied by I. I is the quantity that is varying with time, so it is this. So dB by dt actually is just the derivative of this expression. When you take it, then it is a simple differentiation, and you get this is your flux through this whole loop as a function of time. This is a constant value multiplied by sine omega t. Now look at the left-hand side of the equation, which is the integral over E dot ds. Now, due to symmetry, because I know that the field of the magnetic field within the solenoid here is uniform, okay, and cylindrically symmetrical, then there is no reason for the electric field to be independent of, or to be different as a magnitude at different points here, okay, over this loop. Okay, so the magnitude of the electric field will be the same over all the points on the loop, and it will be tangential, okay, because this is a circle. Why is this so? Because, you know, when you traverse this loop at all points, you will always see the same magnetic field environment. So when it is changing, then I expect to get the same field all over when I move here as a magnitude, okay? But the direction of the field, of course, will be tangential, and I choose it so that ds and E are in the same direction. So I can, when I take this integral, E goes outside as usual, and this becomes integral over ds. Integral over ds is just 2 pi r. Now, it is the circumference of the loop, because I'm integrating over that whole loop. So I equate this to this, and from which I extract the magnetic field, electric field, and this is your electric field. And as you can see, it is a quantity which is varying with time as sine omega t and is dropping as 1 over r as you go away from the t. So the electric field becomes weaker as you go away. And note here that it is in regions greater than r is greater than r. That is, I am outside the solenoid. So in this region, there was no magnetic field. But there is an electric field induced due to the change in the magnetic field in this region. Okay, so this is the thing that we have to learn. Now, the next, of course, calculation would be to find what is the electric field inside the solenoid. This is wrong. This path is wrong. It must be a path within the solenoid, because I want to find the induced electric field at points inside the solenoid, r less than capital R. So this loop, it should be a circular loop, but should be inside the solenoid. Okay, I do exactly the same thing, and in this case there is a mistake here also. Yes, the mistake, it's corrected here. This should be small r. This should be small r. Why is this so? Because now you are looking at the flux through a loop which is within the solenoid. So the magnetic field is not, the flux is not through the whole ring, but through a ring which is a loop which has a radius r. So it will be the magnetic field multiplied by that area. So it would be small r. Okay, and here it is corrected actually. So this should be small r, this should be small r, and so when you take the derivative, the only derivative is the derivative of b. Again, b is equal mu ni cosine theta, and you take the derivative of cosine theta. So this is a correct expression for the time derivative of the flux. It's exactly what we have done before, except you have to note that this quantity should be small r. Again, the left-hand side will be the integral of the electric field within over that loop. Again, due to symmetry, I can take E outside the integral, multiply by 2 pi r, which is the radius of the loop, that the circumference of the loop inside here, and you equate these together, and you isolate now the electric field, and as you can see, you get this expression. Now, this is now an expression which is again varying. Electric field is varying with time, but it's growing with r. So at the axis of the solenoid, the electric field here, induced electric field, is 0. As you go away from the solenoid, axis of the solenoid inside, the electric field increases with r. You can check that at r equals capital R, the electric field from inside and outside are the same. Here, the electric field is induced in a region where I have a magnetic field varying, because within the solenoid, the magnetic field is varying in this case. And so this is the expression that we got. So as you can see, this is an electric field. There is an electric field in this region within the solenoid, outside the solenoid. So if you put any loop now there, then a current will flow through that loop. If you don't put a loop there, you will not, there will be no current. If you put any charged particle there, a charged particle will feel electric force. Okay? So, but if there is no loop there, there is still an electric field. This is the Faraday's law, and this is actually the major manifestation, actually, or a clear manifestation of the fact that electric and magnetic phenomena are definitely not distinct phenomena. Actually, magnetic fields generate electric fields. Later, those of you who will take electromagnetic theory will see that varying electric fields will generate also magnetic fields, and so on. So actually, the magnetic and electric fields are we can say roughly they are the two sides of a single coin. Okay.